Okay, let's see, is everyone here? Almost. All right, let's get cracking. So what do we have to do today? We're going to actually carry on with chapter 7. And we got a lot done yesterday, of course. But I'm also going to show you some nice shortcuts. Okay, I think you'll be excited by that. So why don't we go back and revisit this last question we were looking at? Suppose that the annual return to a stock is normally distributed with a mean of 0.05 and a standard deviation of 0.02. All right, so we saw yesterday that we can actually calculate these probabilities using our normal tables, but first we have to make a conversion because while the stock's return is normal, it is not standard normal. Okay, so in other words, what we have here is, let's say X is the return to the stock. Hold on one second. Let's see. X is the stock return. And it is normal with, okay, the mean is 5% and the standard deviation is 2%. Okay, now we cannot use our charts with this situation because the charts are set up for the standard normal distribution only. So fortunately, there's a way of getting around that. We can use this conversion formula. So what this is basically doing is converting one distribution into the other so that we can in fact use our tables. So in other words, you can visualize that we start out up here with the returns. The mean is 5%. And then we have, because the standard deviation is 2, we can draw it like this. And then let's say we have this point as well. And we'll fill in a couple of the others. Okay. So the equivalent values on the standard normal curve, this is X, this is Z, which has a mean of 0 and a standard deviation of 1, would be 0. Now this one is 1 because it's 1 standard deviation above the mean. This is 2 because it's 2 standard deviations above the mean. This would be represented by -1 because it's 1 standard deviation below the mean. And finally, this one is 2 standard deviations below the mean. So, and again, what we're doing is essentially rescaling these values, just like converting from Fahrenheit to Celsius or something along those lines. So these calculations are being accomplished with this formula. That's how we go from X to Z. And once we have Z, then we can easily calculate any probabilities we need with our tables. All right, now before the rise of these super high-powered calculators, this is really what we had to do to calculate normal probabilities. And we can still certainly do that. If you don't have the calculators, the high-powered calculator, if you have a basic calculator, you can certainly still use this approach. But if you do have the Texas Instruments series, it turns out that it has this functionality already built right into it. So the question is, how do we use it? All right, so now let's try to do this with these 3 probabilities. We've already seen how to calculate these 3 probabilities. And just as a reminder, the probability that X was less than or equal to 4% turned out to be 0.3085. 8% or more turned out to be 0.0668. And this last one turned out to be what was it? Hold on. 0.5328. All right, now, how about if you were going to use the functionality of the Texas Instruments calculators? Here's what you would have to do. Okay, so let me insert this as a new slide. Okay, to compute these probabilities with the Texas Instruments 83 or 84, or one of the higher end ones, number one, you have to go to the right menu. So the menu you need is second. Hold on a second. Second VARS. Now you recall we've used this menu before when we looked up Binom PDF and Poisson PDF. So what you're looking for here is the function called normal CDF. Okay, now that's important. If you recall, with binomial and Poisson, we chose the PDF version. For this one, we're going to use CDF. Okay, there is a PDF function in there. We're not going to use it. Make sure that for the normal distribution, you use CDF rather than PDF. Okay, I'll tell you why. Let me just quickly show you this in the side, what's going on with that. If you look at this normal curve, what these functions are actually doing is this. Let's say that z equals 1, which means 1 standard deviation above the mean. And we want to know the probability that we're below 1. Okay, less than or equal to 1, which means this entire shaded area So the normal CDF function is actually giving us this area. And you notice the C stands for cumulative, which means everything from 1 down to negative infinity. The PDF is going to just give you the height of the curve at this point. And this is not what we want. For certain applications, yes, but not for us. So in other words, don't use this function. You want to use CDF for cumulative. Okay, in other words, not what we did. Remember before with Poisson and binomial, you use PDF, not here. Okay, here, make sure you use the C. All right, anyway, now in order to use this normal CDF function, we must supply 4 values. Okay, now, keeping in mind that all these normal probabilities are calculated as ranges. So let's just go back to this one for a second. When I calculate this probability, in principle, what I'm actually doing is this. Okay, so it's implied, when I write it like this, it's understood that it goes all the way down to negative infinity. But if you write it like this, then it's clear that we actually have 2 values in this interval. This is what we will call the lower limit. And this is what we're going to call the upper limit. So for each probability that we calculate with the calculator, we need to tell it the value of the lower and the upper limit. All right, so we need to provide it with 4 pieces of information. Number 1, the lower limit of the interval, 2, the upper limit of the interval, 3, the mean of the distribution, and 4, the standard deviation of the distribution. Okay, so for that example we were just looking at, so given that the returns to the stock are normal with a mean of 0.05 and a standard deviation of 0.02, we can calculate this first probability, 4% or less, which means actually it's X, sorry, we're using X now. Okay, so remember, X is used for the normal distribution, but Z is reserved for the standard normal, We don't have the standard normal here, so we'll use the X. So what you're going to do is if you go to normal CDF, you'll notice it's going to ask you for 4 things. Okay, so it's going to ask you in this order: lower, upper, the mean, which you'll see is the symbol mu right there. And then we will also need the symbol for sigma. Okay, so here's what you would do. Now, again, remember that we're going down to negative infinity. Now, here, since returns to stocks can be negative, what we're going to do is put for our lower limit negative infinity. Now, there's just one problem here. Let's see if I can find the symbol for infinity. Ooh, maybe not. All right. I'll tell you what, there's a workaround for that. Hold on. Oh, actually, that only works in Word. Hold on a second. Watch what I can do. So the code is 221E. If I hit Alt-X, voila, there's my symbol. Okay, great. Oh, it's so tiny. Hold on a second. No, it doesn't want to get any bigger. What is that? Oh, no, there it goes. Okay, so the lower limit is technically negative infinity. The upper limit is 0.04. Because remember what we're aiming for. Just remind ourselves, we're looking for x less than or equal to 0.04, which is the same thing as saying between negative infinity and positive 0.04. So the lower limit is considered to be negative infinity. The upper is 0.04. The mean in this case, remember, was 0.05, and the standard deviation is 0.02. Now, there's just one more issue we have to deal with here. What to do about this negative infinity? The calculator doesn't have an infinity button on it. So there's a workaround for that, though. What we have to do is use instead the smallest number that the calculator is capable of representing. There is no infinity button on the calculator. The workaround is to use the smallest number that the calculator can represent for negative infinity, which is negative 1.0 times 10 to the 99th power. So how do we represent that on the calculator? Okay, this is entered as, okay, so you hit negative second comma 99. This will show up as negative E99. All right, so if you go to the lower limit on your calculator and you type negative second comma 99, actually, I just noticed something. It might also show up as negative 1E99. It depends on which version of the calculator you have, but either way, this represents negative infinity. Okay, so therefore, we can go ahead and replace this negative infinity with negative second comma 99. And if you go through all those steps, it should give you the answer, which we already have seen. Okay, which is, it was 0.3085 if I remember correctly. All right, so let's type in those numbers and let's see what we get. And that should be, yeah, 0.3085. All right, so once you get used to the setup, I think you'll find that this is much quicker and easier than using the tables. But it's up to you. You can do whichever one you want. If you don't have a Texas Instruments or something comparable, you'll have to still use the tables. But if you do, you might as well take advantage of it. So what about the other two? We also were asked to calculate the probability that X is 8% or more. So that would be this case. X is greater than or equal to 0.08, which, hold on a second. So what you're really looking at here is an interval between 0.08 and positive infinity. Okay, so this is a different situation because we're looking for areas to the right. In other words, where the mean is 5, we're looking for the area above 8. Okay, so we have to change interval. Now this one, remember, was everything from 0.04 down to negative infinity. No, hold on. There we go. That's a little better. So remember, the mean was 5%. We're looking for everything below 0.04. That means all the way down to negative infinity. Whereas here, we're going up to positive infinity. Okay. So that means the interval that we're looking at is actually everything between 0.08 and positive infinity. So now the lower limit is 0.08. The upper limit is positive infinity, which is just, instead of negative, second comma 99, it's just simply second comma 99. And this comes in, and when you type this in, you'll notice that it either lists it as E99 or possibly 1E99, depending on which version of the calculator you have. Like here, for example, we had either negative E99 or negative 1E99. It means the same thing. So then you plug in, these two don't have to change. The mean is the same. The standard deviation is the same. So if you type in all those values, what do you get? We'll go from 0.08 to positive infinity. And then you run it and you get 0.668, which is exactly what we had before. Now, once in a while, if you use the tables in the calculator, you'll notice there could be some subtle rounding differences, but they're usually quite small, so we don't really have to worry about it. So in other words, using the tables, we did actually get 0.0668 here. Occasionally, like for this one, there's a chance at least that you might get a slightly different value in the calculator, but that would be because the tables can only show a certain number of values. And then finally, we'll finish up with the last one, okay, where we had to calculate a probability that X is between 4 and 7%. Okay, between 4 and 7. Okay, so this is one of those in-between problems where with the tables, we have to calculate two different probabilities and subtract one from the other. Now here, this is, you can enter this directly into the calculator, and now you don't even need to mess around with infinity because it's simply the area between 0.04 and 0.07. So now for this graph, we're just literally looking for the area between 0.04 and 0.07, where 5 is in the middle. Okay, so when you throw those numbers into your calculator, all right, so lower is 0.04, and 5328 is our answer. And that's it. So those are three classic examples of how to calculate normal probabilities with your calculator. So I think you'll agree that's a little bit quicker and easier than using the charts. Okay, but just keep in mind that calculators have only been around for a relatively short time. So throughout history, we use charts, and only recently have we been able to use these wonderful calculators. So going forward, you can choose either approach. It doesn't make any difference, but it's important to get some skill with this because we're going to see this normal distribution over and over and over again throughout the course. And in fact, if you get onto a more advanced course in statistics, you're going to still see it over and over and over again. Okay, so you never know when that might happen. It's possible. Suppose you decide to major in statistics or something, it could happen. All right, so with all that being said, we're going to introduce a fairly, this is actually not as useful as it was before computers and calculators became readily available. But the motivation here is that it turns out that the binomial distribution is closely related to the normal distribution. If I can maybe draw some pictures here. Actually, you know what we could do? Let me go get the last chapter for a second. Chapter 6, I mean. And I just wanted to show you something very quickly, or remind you of something. You might recall we had graphs in here in chapter 6 of the binomial distribution. And so what I'd like to point out here is that if you look at the chart where pi equals 0.5, or any of them really, but especially that one, if you look at it very carefully, if you could imagine that instead of having 10 trials for this experiment, suppose instead we had 100,000 or some enormous number, what's going to happen is that you're going to get a lot more of these little bars. And already you notice these bars kind of look like something that we just looked at. Let me just try to fill this in a little. And you'll see that, guess what? It looks like the normal distribution. Okay, so in other words, if we continue to increase the number of trials, the binomial distribution eventually, in the limit, converges to the normal distribution. So you can think of the binomial distribution as sort of a discrete time version of the normal distribution. So because of that, in cases where we want to save ourselves some time, we can sometimes use the normal distribution as a substitute for the binomial distribution. So you're probably wondering, why would we ever want to do that? Okay, so just as a quick example, this approach can be useful when there are many trials to an experiment. For example, suppose a coin is flipped 100 times. What is the probability of getting between 50, let's say 45 and 55 heads? Okay, now using the binomial distribution, we know how to do this. It won't be that difficult because all you're really doing is this. So you go ahead and you apply the binomial distribution to each of these probabilities and add them up. And you might say, well, what's the big deal? Well, that's 11 calculations. That's going to take a while. And what if we needed, let's say we flipped the coin 1,000 times and we're looking for the probability of getting between 450 and 550 heads. That's really going to take a long time. So in cases like that, it might be quicker and easier to come up with an approximation based on this normal distribution. All right, so here's a good example. Suppose that we were told that in the population, the general population, 8% of all people have type AB positive blood. We have a class of 60 students, and we want to know the probability of getting between 3 and 7 who have type AB positive blood. Now, clearly, this is a binomial experiment. If we think of the blood types as either being AB positive or not AB positive, then we can think of this as a binomial trial, even though, or binomial experiment, even though obviously there's more than 2 blood types. If we're willing to think about success as AB positive and failure as all the rest, and you might recall from high school biology that that would be A, B, O, A, B, and then they all can have pluses and minuses. All right, so that's, in other words, everything else except AB positive is going to be considered a failure. So we're just looking for AB positive. This is the rarest blood type, so therefore we're interested in studying this, let's say. So we know that in the general population, 8% have this type. So we're going to define the probability of success, which we call pi, to be 0.08. We also have 60 students. Each one is a trial, in effect. Each person is either AB positive or they are not. So therefore, we can think of this as a binomial experiment, and we can calculate any probabilities that we need using the binomial distribution. Well, what's the problem? Well, we need to do all these different calculations. We're looking for the probability that the number is between 3 and 7. So you might say, well, you know, I can do that, but guess what? That's a lot of calculations. Why don't I instead use this technique? Why don't I use the normal distribution instead of the binomial? It'll save me some time. All right, well, that's fine. Now, this requires us to go through the following steps. The first thing we need to note is that we are actually taking a discrete distribution and approximating it with a continuous distribution. So we have to make some adjustments as we go along. One of them is this, the so-called continuity correction. What we're trying to do is improve the approximation, because remember, we're using a normal curve to represent a series of bars, and there's bound to be some inaccuracies when we do that. So what we're about to do is designed to help overcome this problem. So the interval that we're aiming for is this. We're actually going for the interval between 3 and 7. Remember, X is the number of successes, which in this case equals students with AB positive blood. By the way, that reminds me, this is a golden opportunity for another poll. Just for the fun of it, what the heck? Let's do a little quick survey, a little non-scientific survey. Ignoring the O's, and the negatives and positives, let's just see what we come up with. Okay, we don't, all right, we can do the negatives and positive too, but let's just forget about that. Just the letters. Let's see what we've got. Okay. So let's try that. Just for the fun of it. It's always fun to have a poll. Oh, we do have an AB. Okay, we don't know if they're positive or negative, but so O is pretty common. Okay, well, that's interesting. I'm not sure how closely this corresponds to actual percentages in the overall population, but I'm not surprised to see the maximum is O and the minimum is AB, because AB is the rarest, O is the most common. All right, well, that was kind of fun. In classes I've had in the past, though, interestingly enough, I've always had a few people who ended up saying, I don't know. I should have put that in there as a choice. I was a little surprised to hear that. People who actually don't know their own blood type. That's not a good situation. If that's you, then find out, because you need to know in case you need blood. But anyway, all right, so that was interesting. So let's go back and carry on here. Now, how do we actually go about this? So the continuity correction is designed to improve the approximation, and what you're essentially doing is you're taking your interval and you're basically widening it up by subtracting a half from the lower limit and adding a half to the upper limit. Okay, so in other words, we started out our case with this interval. And then what we're going to do is change that to 2.5 up to 7.5. Now, and again, the only reason for doing this is to improve the approximation, because it's understood that what we're doing is only an approximation, but we want it to be as close as possible. And by the way, just as a side note, if one of your limits is either positive or negative infinity, this step is not needed. In other words, you can't add or subtract a half from infinity. It stays infinity. So if you have a whole number of some kind, then you certainly want to apply this. But if you have infinities involved, then for those two cases, you do not need to do this, because it doesn't make any sense to add a half to infinity, for example, because it's still infinity. So it's only when you have actual numbers here that you need to do this. All right, now once that's done, what you can do, if you want to use the chart, you can use this new formula. Now remember, this is the equivalent of what we did here. And the reason why it's set up this way is because if you recall, the expected value for the binomial distribution the mean or expected value is n times pi, and the standard deviation is the square root of n pi 1 minus pi. So basically, it's the same formula where we've replaced mu and sigma with the equivalent formulas taken from the binomial distribution. Okay, so even if you're not using the chart, though, you still have to calculate these values, okay? In other words, you must use for the mean that is entered into the calculator, you have to replace it with n times pi, and the standard deviation has to be replaced with this expression. So you need to do something like this, whether you use the chart or not, okay? So what happens, what about our case? All right, let's see how this works. So we have 60 students, each of which has an 8% chance of having AB positive. Okay, so n times pi would therefore be 4.8. And the standard deviation, which is n times pi times 1 minus pi, would be approximately 2.101. So in other words, what we're basically saying is that we are treating x as a approximately normal random variable with a mean of 4.8 and a standard deviation of 2.101, and we're applying it to this interval, 2.5 up to 7.5. Okay, so let's do it. Now, if you apply the chart, if you want to use the charts and you actually apply this formula, what you're actually doing is you're going to wind up with this. So in other words, the probability of being between 2.5 and 7.5 on this distribution is equivalent to being between negative 1.09 and positive 1.29 on the standard normal curve. All right. Now, if you go to the charts, now remember, this is an in-between calculation. If you go to the chart and look up 1.29, let's see, let me go find that chart. Okay, so for the positive side, we're being asked to calculate the probability that z is less than or equal to 1.29. So how do we do that? So we need the 1.2 from over here. We need the 0.09 from over here. And at their intersection, you'll find 0.9015. Okay, and that's what we have here. For the negative 1.09, we do the same thing on the negative chart. So we need the negative 1.0, which is way down here somewhere. There we go. Negative 1.0 and 9. When we bring those together, we get 1379. All right. So that's our 13. So we subtract them and we end up with this number. Now, if you want to use the calculator directly, let me go back and grab one of those other slides that I created. Here we go. We'll pick one of these at random and recycle it, I guess we could call it. Okay, so we're looking at, so we already know that it's approximately 7636. Now, if we do it with the calculator, we'll probably get a slightly different number because, again, we've been rounding based on the charts. So here we've got 2.5 up to 7.5, where the mean, if you recall, is 4.8. And the standard deviation was 2.101. Wait a minute, that can't be right. No, my mistake. It's 4.8. It's not 0.048. It's 4.8 and 2.101. But the interval we're looking for is between 2.5 and 7.5. So the lower limit is 2.5. The upper limit is 7.5. All right, now we got it straight. So in other words, you're looking for the probability being between 2.5 and 7.5 when the mean is 4.8 and the standard deviation is 2.101. All right, so remember the mean is 4.8 and we're looking for a value between 2.5 and 7.5. Okay, so if you plug those into your calculator, let's see what we get. All right, so let's go back to the calculator. All right, we're looking for the range between 2.5, 7.5, when the mean is 4.8 and the standard deviation is 2.101. So on my calculator, I'm getting 0.7638. Okay, So as I expected, it is slightly different than what we got from the chart. Okay, with the chart, we got 7638. With the calculator, we got 7630. So wait, this is, sorry, 7636. Here we have 7638. It turns out that the exact probability based on the binomial distribution is 7639. Not bad. I think you'll agree that that approximation worked out very, very nicely. Now, in general, the approximation doesn't always work out well. We have to be careful when we use this thing. If the expected value or the mean, n times pi is at least 5, and n times 1 minus pi is also at least 5, that is going to give us a pretty good approximation. Now, in our case, n times pi was actually only 4.8. But, that's awfully close. I think you'll agree. And then n times 1 minus pi, well, that's clearly well above 5. 0.92 times 60 is 55.2. So we had nothing to worry about. So you can see, according to this rule of thumb, we should expect to get a very good approximation, and we certainly did. Okay. It doesn't have to be exactly 5, but we're pretty close. All right. Now, of course, you can see how the usefulness of this is greatly reduced at this point in time, because we can do all of this in on our calculators. And of course, Microsoft Excel can do this very quickly and easily. In fact, just as an aside, this is not, because you don't have to do this yourselves. I just want you to see how this works. Suppose you have right in front of you a copy of Microsoft Excel, and you're saying, you know what? I want to try this in Excel. And you say, all right, let's go back to the original problem. All right, so we have N is 60 students, pi. I think this thing is capable of doing symbols. Why, there they are. How do you like that? 0.08. So what we need to do is calculate the probability of getting between 3 and 7 students who have type AB positive blood. So here's what we'll do. We'll have a chart for 3, 4, 5, 6, and 7. And then in each of these cases, I will calculate the binomial probability using Excel's functionality. It's in Excel, it's spelled binom.dist, which you can actually use this insert function box to do this. The number S is the number of successes. That is in this cell here. The number of trials is 60. That's in cell B1. I'll use dollar signs to lock in that reference. The probability of success is in cell B2. And then the cumulative probability, this is 0 for no. These are not cumulative probabilities. So now I just have to add them up, and I'll get the actual exact answer that I need. Yes, it's about 7639, roughly. If you round it to 4 places, as it says in the slides, the exact probability is 7639. And so we did a pretty good job. So you can see now the normal approximation is not as useful as it has been in the past, but it's still useful for certain types of applications. It's comfortable. I mean, it's good to know that the two distributions are so closely related to each other. And we'll see this pop up again later on anyway for other applications. So if you're not using Excel now, if you're majoring in any business discipline of any kind or economics, probably you should at least try to start learning Excel as soon as possible, because it's going to come in very handy with your future business classes, but also in the job market. Yes, that's right. Employers want you to know Excel because they do so much of their work using Excel. So this is just a simple application, but you can see how powerful it really is. And if it didn't matter if it was 3 through 7, if I needed to do 1,000 of these, it wouldn't have taken any more time, because I just would have had to copy the formula add them up, and I'm done. So that's one of the nice things about Excel. It's very, very powerful. It has a lot of functionality built into it from finance and statistics. And so the sooner you get to know it, the better. So, all right, that means it's time for another poll. Let's try this one. Oh, it's being a pain. Why is it not letting me do a new poll? Huh. Wonder if there's a limit to how many I can do. Well, we don't need these anymore. But I don't see any way of getting rid of them. Oh, here we go. I mean, after 3 or 4 attempts, it's finally letting me go on to the next one. Well, that's very thoughtful, I must say. Okay, now when I say use Excel, I don't mean like every day, but just even occasionally. Wow, I'm impressed. I have to tell you, I'm impressed here. I find constantly when I'm speaking to college students about Excel, many of them are like, what do you mean Excel? I don't use it. Well, I'm glad to see this because this is, as you already know, then if you're using Excel, you already know how powerful it really is. It's like you've been admitted to a secret society where you all know how to use Excel. Um, yeah, so I'm glad to see this. And the rest of you want to get started sooner rather than later because I guarantee you it'll come in handy. And it's not hard to learn. God only knows there's a million videos on YouTube that you can use to get started with it. So, and there's also dummies books out there that you can use if you want to. All right. So now there's another, I think there's another example in the slides. Let's take a look at that. Oh, okay. So we're going to use the same setup, but now we want to know the probability that no more than 6 students have type AB positive blood. So in other words, between 0 and 6. Okay. Now the continuity correction, in a case like this, we're not going to adjust the lower limit because we can't get below 0. So what we're going to do is instead is we're going to replace this with 0 up to 6.5. Now the rest of it is exactly the same. Okay, the mean, the standard deviation, nothing has changed. So if you're going to use the tables, what you're actually doing is converting. And that will give you 0.81. So in other words, we're technically leaving off the left tail, but it doesn't really matter because this area is so small. And is over here, we're just going to leave it as 0.81. Okay, so again, you can see we're going to have some approximation errors, but we should get a pretty reasonable answer. So this gives us 0.7910, where the actual answer is 7980. If we want to use our calculators, which we probably should, if we can, what we have here now is the range between 0 and 6.5. So let's see what that gives us. Let's see. Okay, so the lower is 0, the upper is 6.5. And that's 0.7796. Ooh, so you can see we're losing some approximation here. It's getting a little bit off. So you can see, yes, we can run into issues with this. 77, that's not that far off. But, you know, the exact probability is 7980. And we got 7796. I think partially that's because of the zero business. If we replace this with negative infinity, we'd probably get something a little more accurate. All right, one more time. At least 4. So at least 4 means 4 or more. Now, in this case, we only have 60 students. So what we're going to look at is everything from 4, and we really should chop it off at 60, even though that does not include, it doesn't take us all the way to infinity. Because we only have 60 students, we can't really let it go any higher than that. So what we probably should do, with the normal distribution though, if we make the conversion, we're looking for everything from negative 0.62 up to infinity, which gives us approximately 0.7324. Because remember, the tables are only showing us what's going on in the left tail. We're after what's going on in the right tail. So why don't we, all right, let's do this with our calculators. And then I'll show you the corresponding value in Excel. How about that? Here we go. All right. So this time, after using the continuity correction, it's actually going to be between 3.5 and 60. All right, let's see where that leads us. Okay, so let's get out the calculators. So it's going to end up being about 73, let's say 20, which is not bad. Since the exact probability, oh, it's 7171. Wow. So we're getting off a bit here, aren't we? And it's, again, it has to do with the upper and lower limits and the continuity correction. So let's go back to Excel now. And remember, we want to know at least 4, which means literally everything from 4 up to 60. Okay, so what we're going to do is come over here and create a new table. We need, sorry, from 4 to 60. Now watch how ingenious this is. I don't have to type all the numbers from 4 to 60. Watch what happens. As long as I've set up a pattern, it understands that I want to keep increasing by 1, and I can drag it down to 60. So you might say, oh, what a headache this is. No, it's not. Look how easy that was. And then I'll use the same formula, equals binom dot dist. The number of successes is here. Number of trials is B1. The $ means I'm linking or locking that reference to that cell so it doesn't change. The probability of success is in B2, which I'll also use $ for, and then cumulative is no or 0 in Excel. So I watch how quick I can fill these in. Watch, I just double click, it fills them in. Now you can see all these probabilities. This is scientific notation. These numbers are so small that Excel has to express this as scientific notation. This is 4.4 times 10 to the minus 5th power. So for all practical purposes, chopping off, as we did, everything past 60 is making no difference at all because these probabilities are really, really, really small. So when we add them up, the total probability turns out to be 7171. Okay. So yeah, it's off a bit. All right. But it's not terrible. It's not bad. Now, again, if you didn't have Excel, this could be the quickest and easiest way to come up with a very good first approximation to our solution. But in this day and age, of course, now we have access to all these amazing tools. Most likely, you'll not need this very often, but it will occasionally show up in different kinds of applications. All right, now it turns out we're not going to cover this case, but you can also use the normal distribution to approximate the Poisson, but we're just not going to do that here. But it is possible to do that one as well. So now that you've seen Excel's power, the people who are not using it now, I think maybe they should change their minds. And you can say, wow, look how easy this is. Man. All right. So now that wraps up chapter 7, which is our discussion about the normal distribution. But of course, like I said, we're going to continue using the normal distribution throughout the rest of this course. And in fact, anytime you take a statistics course in the future, no matter what level it's at, you're going to use the normal distribution for many, many of your applications because it works very well in practice. Okay, it's very convenient and it does a good job of explaining what happens in reality. Okay, so with that being said, the next chapter is 8. By the way, just a quick reminder, not that we're going to do anything about this just yet, but the second midterm is actually based on chapters 6 and 7. So theoretically, we're already ready for it, but we're not going to dive into that just yet. Instead, we have problem sets that we're going to do first. There's on Moodle a problem set for both 6 and 7. Let's go get Moodle open. Okay, so yes, down here we have chapter 7 problem set. We have chapter 6 up here, problem set. All right, now, you know what? Let's get take a peek at the calendar. Now, already, you should have already handed me in the problem 3 and 5 sets. I'm still working on correcting them, by the way. I'll have them back very soon, but those were due on last Thursday, as a matter of fact. So your midterm isn't due until the 11th. So you got plenty. Your first midterm is not due to the 11th. Because we're, obviously getting towards the sort of the latter half of this course, why don't we do this? How about, because we need to go over them before the second midterm, why don't you add to your list? How about if we have chapter 6 and 7 problem sets also be due on Monday the 11th? I think that should give you plenty of time to finish them. And then we need to go over them quickly before we have the second midterm. And then the final, since our last official day is the 19th, I can give you the final then, or you could, well, let's just put it this way. Since our last day is the 19th, the grades probably aren't due until the following Monday. So you could actually hand in the final like later this week. So, all right, I want to make sure everything doesn't get too bunched up though. So let's do this. Let's tentatively choose the 11th as the due date for, in fact, I'll make an announcement right now. All right, so Monday, January 11th, the following are due. Midterm number 1, and I'll put in parentheses based on chapters 3 and 5. Chapter 6 problem set and chapter 7 problem set. Okay, that's good. And then I guess this week we could, then I think what that means is that on Monday the 11th, what we probably should do is start reviewing for the second midterm. Okay, that sounds good, because then in the meantime, we can carry on with chapter 8 and possibly begin chapter 9, depending on how far we get. And then after the weekend, when you've handed in those 2 problem sets, you will be ready to go over the second sample midterm, which is, where is it? It's here. There it is, the second sample midterm. In fact, why don't we open it up real fast and I'll just show you what it's all about. So this is just 6 and 7. And you've got all these wonderful topics that we've been covering. And so, these are the solutions. Oops, we don't want you to see those, but there's fill-ins and there's problems and, okay. But it's all based on what we've just been doing. Okay, so. Okay. All right. So, all right. So let's have our break. And then when we get back, we'll start chapter 8. How about that? Okay. All right. In the meantime, I just noticed, I think I made a mistake here somewhere. I've got to edit this. I think I accidentally posted the solutions there. So let me get that out of there. No, I know we want you to have the real version. So I'll take care of that later on. But in the meantime, yes, what we should focus on is chapters 6 and 7 problem sets. Oh, mu comes from the problem. They have to tell you, or either that, or in the case of the binomial approximation, it's the product of n times pi. So either they have to tell you n and pi, or else they have to give you the value of mu. You can't figure that out for yourself. And the problem, chapter 6 problem set, you can send it in by the 11th, or earlier is fine too. Okay, so we'll make those all due on the 11th. The first midterm, the chapter 6 and the chapter 7 problem sets, you can have them all in by the Monday the 11th. Okay, are we good? Excellent. Okay, so see you in a bit, and then we'll start chapter 8. All right, so I guess we will carry on now with chapter 8. All right, now chapter 8 is directly related to the normal distribution. It's a different type of application. We're going to actually go back and revisit the notion of samples. Now, of course, we all know what a sample is. A sample is simply a subset of the population. Now, what's interesting about samples, though, is that if you imagine yourself repeatedly drawing samples, let me just add this in here. Okay, so when each time a sample is drawn from a population, the data obtained, I guess, or we could say the values that are obtained will be different each time. Okay, so in other words, if you're randomly sampling people, and let's say you're asking them their ages, every time you pick a new group from the population, you're going to get different numbers. And so what that means is that as a result, each sample is likely to have a different sample mean. All right. So in other words, if I just keep randomly picking people, let's say I'm standing at the mall and waiting for people to walk by, and I, randomly pick 10 people and I ask them their ages, I calculate the sample mean. Then I do the same thing over and over and over again. Each time I do this, the chances are pretty good that the sample means that I get will be different from each other. Well, that being the case, what we can do is think of, wait a minute, where am I? For this reason, choosing samples from a population can be thought of as a random experiment. The means, or the sample means, that are obtained from this experiment can be thought of, or I guess what I should say is the value of the sample means that are obtained from this experiment can be thought of as a random variable. Okay, in other words, you can imagine that X represents the mean age of the samples chosen. So if that happens, once we have a random variable, it will have the following properties. This random variable will therefore have a probability distribution as well as a mean or expected value, a variance, and a standard deviation. So we will define the means the sample means obtained by choosing samples from a population will represent a special type of probability distribution known as a sampling distribution. Okay, so in other words, what we're doing here is we're creating a very special type of probability distribution, which is known as a sampling distribution. Now, we can do the same thing. A sampling distribution can be created for any sample statistic. In other words, sample mean, sample variance, samples, standard deviation, etc. And we'll actually see some of these later on, but the sampling distribution of the sample mean, or X bar, is approximately normal. Okay, now that's the tie-in right there. This distribution that we're creating by calculating sample means is approximately normal. And that's a huge deal because that makes it easy to calculate probabilities for these sample means. So for example, this makes it possible to compute probabilities for sample means. For example, suppose that we randomly choose 10 people at a time at the mall and ask their ages. We then compute the mean for each sample. So what we can do now is say, all right, the sampling distribution enables us to compute probabilities such as, what is the probability that the means of these samples are, let's say, 30. So if I want to know that probability, I can do that because I'm creating a probability distribution from these sample means with very specific properties, including the idea that the distribution is normal. Okay, so now what we have to do here is define some of the key properties of these sampling distributions. So for example, we'll start by noting that there's many different ways in which we can actually create a sample. For example, here we're seeing that suppose we choose our samples in such a way that every member of the population is equally likely to be chosen. In that case, we have what's called a simple random sample. And this is the approach that we'll typically use in this chapter, a simple random sample. Everybody is equally likely to be chosen. Now, of course, there are many other kinds of samples that we could choose, but we're not going to do that here. Usually, the thing about economics and finance is that you can't realistically conduct experiments like you could in a science like biology, let's say. So because of that, we basically have to be very careful with the way we choose samples because we don't have any control over what turns up in our samples. So the best approach is often to simply use one of these simple random samples because it's easy to understand the properties of these samples. In other areas, like let's say psychology, where they're looking for very specific things or characteristics, let's say, in people that they choose, there are different ways of choosing samples, but we're not going to approach any of those here. We're just going to stick with simple random samples, which keeps everything very down to earth and simple because we really don't need any of the more sophisticated techniques. Now, before we do that, we're going to define a couple of key words here, key terms. We haven't done that in a while. The word parameter represents a summary measure of a population. And we've already seen these before. The population mean mu and the population standard deviation sigma are examples of parameters because they represent the properties of a population. Then we have the formal definition of a statistic. A statistic is a summary measure of a sample. So therefore, X bar and S are statistics because these are measures that are taken from a sample. All right, so now, all this time into the course, you actually know what the word statistic actually means. All right, it took a while, but we finally got around to it. This is what a statistic actually means. a summary measure of a sample, such as X bar and S. Okay, well, now that we got that straight, and as I mentioned, if samples are repeatedly drawn from a population, the value of a statistic such as X bar will vary from one sample to the next. As a result, that X bar statistic can be thought of as a random variable, and its properties can be described with a probability distribution. But it's a specific type of distribution, which is known as a sampling distribution. And it's called that because it's generated from samples rather than a population. Okay, so in other words, it's clear, it should be clear that this distribution comes from samples, not directly from the population itself. All right, so here's an example. What if I pick 5 people at the mall again, and I write down their ages? So here we go. This is the result of my hard work today. I went down to the mall and I chose 10 samples of 5 people each. Each person is identified as either X1, 2, 3, 4, or 5. I want to keep this anonymous. Let's say I don't have their actual names. And so in sample 1, I ended up with a mean of 35.2. And these are the actual ages. In sample 2, I've got a mean of 55.0. In sample 3, I've got a mean of 52.6, all the way up to sample 10, where I wound up with 55.2. So the key detail here is that each sample is different. And as a result, the sample means are different. So by using these samples, these sample means, I can create a probability distribution for the means of these samples. Okay, now, what I've done is I've created a bar graph, a histogram, to show you the distribution of the ages that I obtained. Now here, each bar represents a range of ages. You can see I've got 10 to 20, 20 to 30, all the way up to 80 to 90. And you can see the bars are kind of scattered all over the place. Now, here's the key detail. If I've only got 5 people in my sample, then there's a very high probability that the means will be very different from each other. Okay, because I could randomly pick little kids, babies, senior citizens, and everything in between. The chances of the mean of a group of 5 people being very different from another group is pretty high. And you can see these do vary quite a bit. And so this is the reason for that, because the groups themselves are scattered about all over the place. Now, what if I increase the sample size to 20? Instead of only asking 5 people at a time how old they are, what if I go for samples of 20? Well, I hope it makes sense that the larger the sample is, the closer the sample means are likely to be to each other. In other words, the chances of 2 groups of 5 having very different ages is much higher than 2 groups of 20. The more people in your groups, the closer the average age should be. Okay, so that's exactly what we would expect. Now, I did this, I don't have the actual numbers here, but I drew a graph of the result of changing the sample size to 20. And you notice something interesting. We don't have all this random scattering around. Okay, remember here, the bars are all over the place. Down here, they're very close to each other. And if I keep increasing the sample size, these bars will get closer and closer to each other. And eventually, in the limit, we're going to end up with what's going to roughly approximate the normal distribution. Now, it's hard to tell from this case, but if you keep doing this enough times, eventually, as we saw in the previous chapter, that the binomial distribution of closely approximates the normal, here the same thing is happening. Eventually, the distribution of these X bars taken from our samples will be very close to the normal distribution. And that's good because that makes it easier for us to calculate probabilities. All right, now, all of this discussion is coming to us from a very important result in statistics, which is called the central limit theorem. Now, I'm just going to mention it here. I mean, you don't have to memorize any of this, but the central limit theorem is a hugely important result in statistics, which explains how and why a sampling distribution for X bar is approximately normal. So there's two key results that we need to know from the central limit theorem. First of all, if we choose our samples from a normal population, then the X bars that we calculate are also normal, which is very, very helpful. I mean, clearly, if we're choosing elements from a normal population, the results that we end up with have to be normal as well. But what if that's not true, or either that, or we're not sure if it's true or not? It's not always obvious if a population is normal or not. This is something we tend to assume, but sometimes we have to justify it. And there are a lot of formal tests in statistics for determining if a population or sample is normal. But what we're saying here is that if we know that the population is normal, then the X bars that we obtain from our samples also has to be normal. But if they're not normal, or if we're not sure if they're normal, then as long as the samples themselves are at least 30, that's the cutoff point, 30. Once we hit 30, no matter what the underlying population is, then X bar will still be normal. Okay, so in other words, in these two cases I showed you before, with such small samples, unless we know for a fact that the underlying population is normal, there's no guarantee that these X bars are normal. But if we have a large enough sample, at least 30, or if we're choosing samples from a population that's known to be normal, then our X bars will also be normal. And by the way, if that's neither one of these conditions is true, let's say that we have a population that is not normal and our sample sizes are small, then we cannot use the normal distribution to calculate our probabilities. We have to try something else. Now, that something else is very complicated, and we will not do it here. But remember, the normal distribution is a very simple distribution to work with. So we like it when this happens. In other words, it's very helpful when our distribution is normal. Okay, but then remember the two key things. The underlying population is normal, then we're all set. Or else if the sample size is at least 30, then we don't have to worry about this. Then we know that our sample means will be normal, which makes it much easier to calculate probabilities. Okay, so then in either of these is true, it just has to be one of these, not both. Then we can go ahead and use the normal distribution to come up with probabilities for our sample mean. Okay, so again, remember we're creating a special type of probability distribution with our sample means known as a sampling distribution. Now, because this is a probability distribution, it has moments. Okay, moments. Remember, all the distributions we've looked at had moments. In fact, let's remind ourselves real quickly what moments we already know. So just as a quick review, maybe I could create a little chart here. We have the expected value, we have the variance, and we have the standard deviation. We'll start with binomial. Okay, we have n pi 1 minus pi, and square root n pi 1 minus pi. For Poisson, we have lambda. This is a really easy one. And then for the normal distribution, we have mu, sigma squared, and sigma. All right, so every probability distribution has its own moments. Now, the sampling distribution that we're creating here for X bar is no exception. Its moments are actually derived from the normal distribution, but they're also a little bit different. Okay, so they're different in a couple of important ways. Okay, so they're the same three. Now, here I do want to point out one detail. And this comes down to terminology. You know how it is in statistics. There's often many different terms that actually mean the same thing. For example, we have already seen that expected value and mean, and average for that matter, are all the same concept. The variance just goes by that one name, but now when we're looking at a sampling distribution, for whatever reason, I don't know the reason or origin for this, the standard deviation is frequently referred to as the standard error. So the standard error is a special type of standard deviation. This refers specifically, okay, this is the standard deviation of a sampling distribution. So the reason why we need the two separate names is to avoid confusing them with each other. You'll see why when we define it. So just be aware, when you hear the word standard error, it's the same thing as a standard deviation, but it refers specifically to a sampling distribution. Okay. Well, now, how are these calculated? So keep in mind that we're assuming that we're drawing samples from either a normal population or else we have a large sample. So X bar has its own symbology that we use to represent its moments. In fact, let me quickly summarize these for you. So this is only for sampling distributions, by the way. So here, the moments of the sampling distribution specifically of X bar, the expected value which is often written E of X, will be written as mu. Actually, no, we're going to write it as EX bar. And then here we'll write mu X bar. These both represent the same thing. So in other words, because we need to make it clear that this is a sampling distribution for X bar, the expected value will be written as EX bar or else mu with a subscript of X bar. The variance will be written as sigma squared, but with a little subscript of X bar. Again, so that we know that this is only about the sampling distribution of X bar, and therefore the standard deviation. And again, remember, this is the same thing as standard error, will be simply written as sigma X bar. So we have to keep an eye on this. This notation is needed so that we don't confuse it with the underlying population. Because now we're not dealing directly with the population. Remember, we're dealing with the sample means. Well, now we need to introduce the formulas. Oh, all right. Well, this one, all right, I jumped ahead a little bit here. Let me put it right here. So here's the first one. So what is this saying? That the mean of the sampling distribution equals the mean or equals the population mean. Well, that's nice. I mean, but think about it logically. If I'm drawing samples from, let's say the US population has an average age of 29. If I draw enough samples from that population and calculate all their means, it stands to reason that the mean of all of my X bars would also be 29, because they're taken from a population in which the average age is in fact 29. So these two have to match each other. Okay, now the tricky one, well, the variance and standard deviation, of course, one is just the square root of the other. We're going to introduce now the formula for calculating that sigma X bar. This is the only one that's the least bit tricky. All right, are we ready to see a tricky formula? Yes, we are. Now, this one requires us to make a distinction between what we're going to call a large or small sample. These depend on the size of the samples relative to the size of the population. Okay. So in other words, how large are our samples compared to the overall population? Now, usually the samples that we choose represent a very small percentage of the total, but not always. If we have a small population, then we could actually have a relatively large sample. So the way we define this is as follows. A sample is considered to be large in this chapter, that is, if it represents more than 5% of the total population. Then that implies that a sample is considered to be, well, all right, I'll tell you what, let's write this out with our notation. This can be written in a couple of ways. The sample size is at least 5% of the population size, or you can write this as n divided by capital N is at least 5%. Now, I did mention earlier in the course that we need to make a distinction between lowercase n and uppercase n. And here's a case where we need both of them in the same formula. So that's why we have to separate the two. In other words, we have sample size being lowercase n, population size is capital N. And here's exactly why, because this formula wouldn't make any sense if they were both lowercase n, let's say. So in other words, both of these are the same thing. If the sample size is more than 5% of the total population, that qualifies as what we will call a large sample. So you can probably guess what's coming next. Okay, a sample therefore is considered to be small if it represents less than, or no, all right, 5% or less of the total population. You know what? I think I'm going to have to change this one. I think this is strictly, I wrote this incorrectly. It's strictly greater than 5. All right, that's better. Okay, so there's more than 5% means large. Okay, less than or equal to 5% means small. So I got to fix this. Now this one would now become less than or equal to, and this will be less than or equal to. All right, so once again, more than 5 is large, less than or equal to 5% is small. All right, now that we got that out of the way, Why don't we see what the formulas look like? Let me just show it to you with a little chart. I'd like to have them all together in one place. All right, this should do it. So this is really all about notation to a degree, but now what happens here is that we have sigma squared. Now the sigma without an x bar is taken from the underlying population. This sigma squared is actually the population variance, the population from which these samples are being chosen. Okay, over here, we have to do something to correct for the fact that this is a very large sample. Down here, we're just taking square roots, as you can probably imagine. Okay, so our chart is complete. And that's all four possibilities. All right, I'll give you a minute to write that down. So on the right-hand side, now what's happening on the right-hand side is that the variance and the standard deviation are actually smaller or lower with large samples. So this term that comes after it is actually a value of less than 1. What we're doing on the right-hand side is actually reducing the variance and the standard error to compensate for the fact or explain what happens when we have larger samples. Okay. Now, with all this setup, the questions that we'll be dealing with are actually surprisingly straightforward. All this is just background. Ultimately, when we're done here, we're going to just use our normal distribution. What's tricky here is calculating these two values. This is the only part that's a bit of a challenge. Once we figure that out, then the rest is just the same as what we've always done, which means calculating normal probabilities. All right. So, is everyone done? Yeah, I know there's a lot going on here, but I mean, it's an accelerated class. So anyway, now we're sort of towards the beginning of chapter 8 here. Now, tomorrow's Wednesday. So what we can do is tomorrow we'll back up a little bit and revisit all these concepts one more time, because I know there's a lot going on here. And then what we'll do is start actually calculating probabilities. And of course, just keep in mind that everything we did today with the normal distribution applies here too. We're not going to look at any cases where we do not have normality. That's for a more advanced class. In here, all of our cases that we'll be looking at will be allowed to use the normal distribution. So we'll just get another chance to review how that's done. Now, by the way, that reminds me, since we use the Excel to calculate binomial probabilities, we should probably also do the same thing for normal probabilities. So let me just quickly make something up for you. Suppose we have a normal random variable x. X is normal. Or in fact, you know what? We could go back and revisit that case from chapter 7 with the stock returns. Just because I want you to see this. let's go get that back out again. With the stock returns, we had a mean of 5% and a standard deviation of 2%. So our first question is, what's the probability that x is less than or equal to 0.04? The second one was greater than or equal to 0.08. And the third one was between 4 and 7. Okay, so here's how it works with Excel. The function is called norm.dis for normal distribution, and you need to supply it with 4 things. X itself, in this case, is 0.04. The mean is 0.05. The standard deviation is 0.02. Is it cumulative? Yes. Put a 1 here for yes, or you can type the word true. That's the probability. Now, if you recall, this is what we got in the slides. How about greater than or equal to 0.08? So we'll use norm s-dist, or norm.dist. And again, the mean, or x itself, is 0.08. Okay, there's just one problem here. This is less than or equal to, so this is not going to give us the correct answer. What we have to do is one more step, which is to subtract it from 1. There we go. Because this function norm dist only shows less than or equal to, just like our charts. And then for this one, we have to do this twice, just like we did with the charts. We're going to have norm dist for 7%. And then we do the same thing for 4% and subtract one from the other, just like with the charts. If we get 5328, which is exactly what we got here. Okay, so the normal distribution is also built into Excel, just like the binomial. So I think as we go along from this point forward, we might as well, just for the fun of it, this is not going to be in any of your exams, introduce the Excel versions of these formulas because I think it'll come in handy. Okay, so I'll save this and post it to Moodle just like everything else. So in the meantime, I think we had enough for today. And what I'm proposing to do is post what we've done so far on the Moodle rather, and we'll just carry on from here tomorrow. All right. So, and we're zooming along here pretty well. I'm kind of impressed because I was concerned that we would get behind. We have so few meetings for this class, but so far we've maintained an excellent pace. So I don't think there's any issue of running out of time here, which is always the big issue with these short classes. So anyway, so I'll see you all tomorrow then.
Have a good one.
All right, you too. All right, bye. You're welcome. See you tomorrow.